For those of you that I have not met, I'm Nick McKeown, and I'm going to be hosting the session today. And I'm going to be got the great pleasure of interviewing my old friend and colleague Harry Balakrishnan. Before we get started, though, I just want to make a couple of announcements, just for those of you that don't make it all the way to the end, so that you hear the announcements ready for next time. So we've got the interview today. A hard act to follow, actually, for those of you that watched the recent one where Jim Carose was interviewing the guy from Zoom, which was fantastic. And there's going to be another one in 2 weeks' time. If you can just go forward, whoever's controlling the screen, that's wonderful. The next one is going to be on the 29th of October in 2 weeks' time. And it's going to be the first networking channel student data challenge that Edmundo is going to be driving. And that should be a really good session. So I'm looking forward to that. Okay, well, I think it's time for us to get stuck in. I don't think we need to share the screen anymore. We can just get started here. So hey, I first met Hari in, we think it was 1994 in Berkeley, and that would have been a year after he graduated from IIT Madras in India. And he was a year into his PhD in EECS at Berkeley. He was working on the networking portion of a really interesting project called the InfoPad project. And these two legendary PhD advisors, Randy Katz and Bob Broderson, you probably all know Randy Katz. Few of you probably know Bob Broderson. He'd won many awards for his work in signal processing, switch capacitor circuits, lots of chip design, signal processing, and sadly, he passed away last year. So Harry and I overlapped at Berkeley for 2 years before I graduated, and it was a pretty interesting cohort of graduate students at the time. There was Amin Vadat, Andrea Goldsmith, Srini Session, Vern Paxson, Anantha, who also worked on the InfoPad project and is now the provost at MIT. To be honest, Harry and I didn't really know each other that well at the time. The networking groups at EE and CS at Berkeley were pretty separate from each other, with lots and lots going on in different groups spread across CS and EE. Folks like Dave Messerschmidt, Domenico Ferrari, Randy Katz, Dave Patterson, Tom Anderson, Dave Culler, Eric Brewer, Praveen Varaya, Jean-Paul Ram, Venkat Anantharam. There's a long, long list of people all working on different aspects of wired and wireless networking. It seemed a little odd at the time that the professors didn't really work with each other across ENCS or between theory, systems, and wireless, with a few exceptions. But I think that's why Harry and I didn't really know each other that well. But looking back, they were pretty thrilling times, times of great change. In fact, to put dates into perspective, Harry started his PhD in 1993, the same year that Mark Andreessen launched the first graphical web browser, Mosaic, and the internet was frankly barely known outside of academia. And it was a full 6 more years before the Wi-Fi 802.11b standard was adopted in 1999. Wireless data was still in its infancy. And it had many skeptics, to be honest. It wasn't until then that you could buy a laptop with built-in Wi-Fi. That was 20 years after the first laptop had been built. Can you imagine using a laptop without Wi-Fi now? Be pretty crazy. So, with hindsight, it becomes clear how prescient Harry's early PhD work really was, because it was about the challenges of reliable transport and congestion control in wireless networking. And that seems like a good place to start. So, Harry, welcome. It's great to see you.
Oh, thanks for having me, Nick. It's great to do this.
So, give us a sense of what it was like working on wireless networking back in 1994, when frankly most people had never heard of any of the stuff that we were all thinking about at the times.
Yeah, it was, in retrospect, quite exciting because there were two pretty amazing trends that were converging through the mid and late 90s. And the first was the commercialization of the internet and its growth, particularly with the web, as you mentioned. And then there was mobile and wireless computing. I actually saw the first time I saw a laptop was in I think it was summer '94. I was visiting. I sought an appointment with Randy Katz, who became my advisor, and I went into his office and I saw two things there. I saw a laptop, which I'd kind of heard about. I'd seen pictures of it, never seen one, and picked it up. It was about 10 or 12 pounds. And I asked him, how do you get email? How do you download stuff onto this? And he showed me a serial interface, an RS-232 and and a modem. And I was thinking, wow, it would be really cool if we could get the internet on this. And I immediately went to, if I have a mobile device, I'm not going to want to connect it to an Ethernet or a modem. I'm going to want to carry it around. So then I asked him, so how do we get something moving while you have an internet on? And he said, um, he kind of said nobody knows, which is not actually true. People knew that it was possible and how to go about it. But what we quickly converged on was the engineering was not had not been achieved. The other thing was that I spent my first year at Berkeley. It was a very difficult year for me because a lot of people at Berkeley had kind of taken early retirement because there was some financial incentive to do so. Many of the faculty members who were actually quite active at the time took the package to retire. And so I struggled, like a few other students, to find an advisor. And I'd heard that Randy was really cool. So I would have worked with him no matter what. So he told me he was getting out of RAID and hardware, computer architecture. He wanted to get into mobile computing. And I said to him, without skipping a beat, I said, I've really been wanting to work in mobile computing ever since I came to Berkeley. The truth was I'd heard about it about 10 minutes ago. The other thing that attracted me to him was the second thing I saw in his office was he's American, but an Anglophile. And he had at the corner of his office, he had a cricket bat and a ball, a red,
Yeah.
like a new cricket ball. And I said, I don't know who he is, but I'm gonna have to work for him. So that's started with a great deal of thought. I started my graduate career in the field, but I did feel like right after that, at that first meeting, that being able to get a laptop to move around with
Mhm.
connectivity would be a really cool area to work on without knowing anything about the prior work.
I see. I see. So, I I've been working on networking problems for a number of years since then. I'm a little bit older than you, and I completely missed the importance of wireless at the time. I couldn't imagine they could ever be reliable or fast enough or cheap enough, or that the batteries in our mobile devices would last long enough. Um, to my embarrassment, I can even remember arguing with a couple of colleagues just after I started at Stanford and thought, yeah, this isn't going to go anywhere. Kind of embarrassing at this point. But I do remember sitting in the Stanford library. It must have been about 97, 98. Maybe it was even 99 when they first. Oh, it was a wireless dongle attached to a laptop. And it just dawned on me this is going to be a really disruptive change. And yeah, there you were working right in the middle of it, right from the beginning. That was actually pretty cool. So I want to ask a little bit about some of your sort of formative years and family influence. I mean, your parents are both really distinguished and renowned theoretical physicists, and your sister Hamza is a professor at MIT as well in Department of Aero and Astro, and it's evident that there's a deep scientific intellectual curiosity through your family. Um, and it makes me wonder, first of all, what did you talk about at the dinner table when you were growing up? Was it all physics and academia? But I'm also interested how you think that this shaped your intellectual curiosity and led you down the path of becoming a technologist and a professor.
Yeah, I think both my sister and I are very fortunate to have been born into the family we were born into, because we had a lot of access to, information. We could get, if the book was available in the library and at the universities my parents worked at, we would get it. And a number of people in my family have pretty much been academics. I think that it's an unusual number. I have uncles, aunts, cousins, etc. To me, yeah, there was my parents would often talk physics in the house, even when I was a child growing up. So I kind of felt like it would be really interesting to do. I mean, it would be a combination, like research, as you know, it's a combination of a lot of, not frustration, but, you're not really making any progress. And then every once in a while you make progress. And I would just see that excitement uh, in their faces. I mean, my parents are now in their, actually in their 80s, and they still are writing papers, and they're still excited about, getting a paper paper accepted and published. And that sense of everything about it was familiar to us growing up, like all the stuff about the stuff not working, and then eventually they got some sort of a result, and then they publish it, and then they get reviewer comments, and they're arguing with reviewers. That was part of the process, so it was quite enjoyable. My mom spent a lot of time teaching me when I was a kid growing up, when I was younger, and then my dad wasn't super involved in the early days. I think he needed a certain degree of maturity in my math before he got involved, and then he spent a couple of summers where he would give me exercises to work on, and then I would kind of have to do it. I was intimidated by him at that time, and I would work on it, and then he did teach me a lot about kind of both math and also about how to think about systems, broadly physical systems. So yeah, I'm very grateful to them. It was,
Yeah.
but dinner table was not all science. We spent a lot of time talking
Uh-huh.
about other things, but it was
I
it was
see.
a lot
Yeah.
of fun.
There's probably a lot of people online here with young children who are sort of thinking, how do you inspire them to be curious about the world? Just kind of curious. Any tips that you learned from your parents that you've practiced or passed along to your own kids?
Um, yeah, I think I've taken a slightly different approach. I feel like I'm not as, I don't try to shape what they want to do, but I encourage them to ask a lot of questions. And I think yeah, I had a similar experience. I don't think they were pushing me or my sister to do anything specific,
Hmm.
but uh, uh, yeah, I don't know if I have any great tips as such, but I do think that they encouraged a lot of questions and they would really try to answer questions. And my father would ask me a lot of questions when I was a teenager. I mean, many of the questions I guess he knew the answer to because he would have figured out how to communicate that. But some of the questions I don't think he knew the answer to, and we would end up talking about things related to, and a lot of them were physics related ideas. But I would say that just engaging children in conversation about topics that they're interested in, or
Yeah.
you want them
Yeah.
to be
Uh-huh.
exploring that would be good. I think that there's not really a substitute for talking to them.
So let's go back to your PhD years for a moment. For me, probably for you too, grad school were just the best days. So much freedom, so many interesting, smart people to work with. Um, I'll credit one of my postdocs for making the following observation. And he said, going to that was coming to Stanford, but for me it was going to Berkeley. So for me, going to Berkeley from the UK meant going from an opportunity constrained environment to an opportunity overwhelming environment. There were just so many different things that we could work on, interesting, smart people to work with. Was Berkeley like that for you too, when you were sort of thinking about what to work on?
Yeah, I think the first thing for me when I went to Berkeley was just how unbelievably knowledgeable the professors seemed to be. When I took their classes, it just seemed like they had thought a lot about how to teach. Um, Whether it was computer science, electrical engineering, or some of the math classes I took, I just thought that they really understood how to. They thought about how to teach, and I was quite blown away by it. And then you look around and you find these huge numbers of projects going on, and a lot of it was it was overwhelming. But what I realized was that you need to find the intersection between what you're really good at and what you're interested in. Um, Sorry, what you're really good at on the one hand, and then what might be actually really interesting to you as a
Hmm.
person. And then if that intersection also you luck out with, if it becomes useful, then you've had that successful area to work in. I think I figured out for myself that it's better to be one of the earlier people in a riskier area because it seemed to me there were other people who were better at, uh, in many of the problems, the final word on the problem, like closing an area completely.
Hmm.
And
Hmm.
so I think I would encourage people to think about what it is they're best at. Whether you're good at opening up something, and sometimes it's just not going to work out. Like the area doesn't go anywhere. But if you're good at that early
Yeah.
stage, taking a risk,
Hmm.
then that's a path to take. But there was a lot going on in all these universities, and understanding
Hmm.
what to work on became as important. I remember John Osterhout in my first operating system class. He has a quote which stuck with me, which is use your intellect to ask the right questions, not just to answer them. And it's something where that's something that stuck with me as a valuable piece of insight.
I think it takes us quite nicely onto your what your PhD thesis was about. So I've got the title here: Challenges to Reliable Data Transport over Heterogeneous Networks, Wireless Networks, sorry, and which won the 1998 ACM Doctoral Dissertation Award. And the key contribution of that was the Snoop protocol, which many people on the call have probably read about and are familiar with. But can you explain, through the lens of that time, what problem you were trying to solve with Snoop? What made you sort of come up with it in the first place, and what your thoughts were on how you would put that into practice?
Yeah, so I want to, going back into the 90s, it was not clear cut like today you have Wi-Fi and you have, cellular LTE or 5G, etc. At the time, it was a complete mess because people were proposing wireless in a variety of different ways. So first of all, there was a number of infrared wireless systems people were building, mainly for printing. So your
Hmm.
laptops would actually come embedded with an infrared. There would be no Wi-Fi. Wi-Fi
I
wasn't there.
remember that.
There would be nothing else.
Hmm.
There was an infrared, and you would point it roughly like a remote control, except it could run at I don't remember the rate, a few hundred kilobits a second, maybe a megabit per
Yeah,
second,
probably. Yeah.
if you were
Hmm.
lucky. And then, you would find that there were dead spots in the room. So that was sort of my first experience with like wireless, was getting a printer to work. Uh, and then there were people, there were Wavelan from Lucent came about, I think, in the early 90s, which was sort of the precursor to today's wireless LANs. And you would take your laptop, and by the mid 90s, they had these things called PCMCIA cards, which were like the size of a credit card, but a little thicker. And you would stick this thing inside the card, inside the slot in your laptop. And then you would have this antenna that was pretty large, and you would Velcro the antenna to the back of the laptop. And then there was a company called Metrocom, which was building a metropolitan area network in the Bay Area and a few other cities, many cities in the US, which was a packet radio network, a multi-hop ad hoc, not an ad hoc, but a multi-hop wireless network with lower throughput. And then there was satellite, which of course now has become popular again with things like
Hmm.
Starlink, but satellite was there at the time, except it was only downstream, and the upstream went through your phone line or some other capability. And then there was cellular digital packet data, which is a very early precursor to today. You'd get a whopping 9.6 kilobits per second on a lucky, and I'm going to repeat that, it's kilobits per second on a lucky day. And the vision that we had in this project that Randy led was that you would build a system that would be kind of an overlay. You would have all these different things on your devices, and you would use the best one in the best possible way. So, we
Hmm.
created a test bed, and this was actually kind of a lot of fun. I worked with the other graduate students, Venkat Padmanabhan, Ilan Amir, people like that. And, we started running experiments, and, we would find, and others in the community had also been finding, that you would get wireless bit errors caused by just signal to noise ratios being low, or interference or contention on the channel. And the packets would get dropped not just because of congestion, which is on the wired network. When a packet gets dropped, the assumption it's congestion, but in wireless, it could get dropped because of reasons unrelated to congestion. And so distinguishing between these two things became a difficult problem. So TCPs, congestion control, would react to packet losses regardless of why they happened, as if it were congestion. And
Hmm.
the throughput would plummet by about an order of magnitude. So I developed a set of techniques in the Snoop protocol that they were kind of cross-layer techniques where at the link layer, you would be aware of the higher layer and perform certain local recovery operations that would kind of, if the packet got lost on the wireless, it would quickly locally retransmit the packet, but then prevent the TCP at the endpoint from seeing that loss as congestion. And then it turned out it improved throughput by a huge amount. And I had other things. I worked on packet radio networks which were more where media access contention interacted badly with TCP congestion control. And then on asymmetric networks where the bandwidth asymmetry caused problems for TCP. So a lot of my work was on kind of making TCP's congestion control algorithms function when they're supposed to function, while hiding or otherwise dealing with the vagaries of the wireless part of the internet path.
I see. Yeah, yeah. No, I mean, I remember all the debates about cross-layer at the time. I'm sure you remember them too. People sort of saying, "Oh, this breaks the neat layering model and the sort of architectural elegance." But that seems to have become sort of standard practice now when you want the higher performance or just something that's local to a specific link. Of course, wireless is such. There was when I think back, there was sort of a lasting legacy of your PhD work beyond the wireless work was the sort of two mechanisms, limited transmit and the selective ACT mechanisms. And you worked to add those into BSD. And you must have gone through this sort of thinking that I think many researchers go through when they're doing a PhD, a postdoc, or as an academic. And they're thinking, how much time am I going to devote away from my new research, the new shiny object that I could be working on, in order to sort of develop or get something upstreamed into BSD at the time or Linux, and then be able to get that more widely supported and build a community around it. I'm kind of curious, how involved you were, and can you remember what you were sort of thinking about at the time as that trade-off and that balance? I think people would find that interesting.
Yeah, I think at that time, a lot of the ways in which you would want to get things into the real world was to get it through the IETF RFC process and make it a standard, and then it would get adopted. Or for that matter, the IEEE 802.11 process. So there's emerging standards. So I remember actually, even with not yet talking about limited transmit and selective acknowledgements, but I remember talking to some of the people who were working on the 802.11 standard and showing them my results on the Snoop protocol and TCP, and sort of saying you could do link layer recovery, but it would have to run at a time scale that was much, much shorter than if you were to implement in software, which was the way it was
Hmm.
being done. And so I think that actually influenced the microsecond level local retransmissions that would happen on Wi-Fi, so that you could either do it with the cross-layer approach, or you could do it at a really rapid time scale where the hardware turns around in microseconds with the link layer acts hiding the issue from the higher levels. And I think that was actually useful. And then there were similar things around, the way in which this cross-layer work works is you sometimes have such an impedance mismatch between the wired internet and like the vagaries of the cellular network that
Hmm.
splitting a connection or otherwise, kind of today they call them performance enhancing proxies are the way to go. So I think there's
Yeah.
an impact like that research
Hmm.
led to quite directly. As far as the limited transmit and the selective acknowledgements work is concerned, so SACs had been proposed by Sally Floyd and others in an RFC
Yeah.
a few years ago, but no, a couple of years before, I think, and just got standardized, I think, in '96 as something the IETF said, okay, this is the
Okay.
scheme. And I needed it for my research. I needed it in order to see whether TCP with SAC, I'd written these papers on without SAC, how wireless does and how to improve it. So I needed it for the research, so I built it, and I found no one had done it before. And then I put out the implementation, and I'm told that a lot of people actually use that as a reference into other operating systems and commercially as well. People at some companies that I later learned that they just took that code and ported it over to whatever platform they were in. So that
I
was very
see. Yeah.
gratifying.
Yeah.
But my first experience with the IETF, where I presented results on like 15 or 20 or 30 internet pads. In those days, that was actually satisfying to people to see. And I showed with and without SAC, and there was about a 20% improvement, 30% improvement. So it was good because I think people just decided that, okay, it's working in the real world. So, uh, we should increasingly adopt it. Limited transmit came about because of my experiments with cellular packet data and some of the Metricom modems, where the bandwidth delay product was so low that if the bandwidth delay product, because of congestion or some other reason, the windows are small, it's a few
Hmm.
packets long, then TCP ends up in timeouts. So the idea was to more quickly, without violating congestion control or packet conservation, recover from losses, and that got adopted into a standard. I think most operating systems implemented today. And again, it avoids these timeouts unless you absolutely get, all the packets in a window are lost, in which case you do need to take a timeout.
Yeah, I see. I see. So, I mean, you've always struck me as someone that's not only worked on the papers, the problems, the theory, but also through to prototyping and then commercial systems, and then working with people who are developing commercial systems. And your work on InfoPad clearly was a bright, shining example of that because of the team that was working on it. That was building a real system and a real demonstrator. How did that shape your thinking, and how do you think that projects like that, which are expensive, time consuming, um, how do you think how are they useful for PhD students today? Is that something that you've, and a sort of a dynamic that you've tried to keep up in your own research?
Yeah, I mean, that was, in retrospect, such an unbelievably visionary project that Bob Broderson and his team envisioned. Back in the late 80s, I think they envisioned it in the early 90s, they started it. I was in the second wave of, or maybe the third wave of InfoPad students. But it was the tablet that had most of the computing offloaded to what they called servers on the internet. Today, you'd call it the cloud. And, the form factor of it wasn't that different from an iPad. I mean, of course, it had a
Exactly.
lot
Yeah,
less
it was
computational.
amazing actually. It's so prescient. Yeah, yeah,
Yeah, so unbelievably prescient. And
yeah.
they used, and this is, I mean, by 1994, there were prototypes that, and my job was, I was part of this little networking group that they had called Infonet, and it was to build a link layer for this InfoPad thing
Hmm.
between these base stations. And these radios were being invented, these radio technologies. They had different radio technologies that they were working with, not just commercial ones, but these were research prototypes. And what I noticed was that the performance and they wanted to support a variety of applications. There were real-time speech recognition. I mean, can you imagine in the mid early 90s, they were looking at real-time speech recognition, and they were looking at
Absolutely. I
handwriting
remember that. Yeah.
recognition. And then they were looking at downloading email or files. So there were a lot of different applications that needed different performance, different performance requirements. Some needed low latency, some had high throughput. And I quickly figured out, with the rate of those radios and the types of performance I was seeing, that you needed a link layer to be a little smarter about what the application wanted, that it was not a one size fits all. So that really shaped my thinking. So I think it shaped my thinking about understanding what the application wants in designing your system. And
Hmm.
that thread has run through it to this day. I'm motivated, extremely motivated by applications in designing networks and designing network systems. And so I think it's a very lasting legacy. But as far as the vision for that project was concerned, it's just, I'm in retrospect, I just don't know how they came up with that vision at
And
that
it's
time.
stunning, isn't it? Just to
And it
think,
was
yeah,
so
yeah,
predictive
yeah,
of the future.
yeah. Yeah, you went from there to MIT, of course, and the I just want to take a moment about learning how to be a lecturer, a teacher, teaching in the classroom, and being a mentor and an advisor to lots of PhD students. Something that, frankly, you become a professor with no training in how to do any of those things. You've got to figure it out on the job. And so, what do you think are the most important qualities of a good advisor in a technical field like ours? And what do you hope that your students take away from the time that they spend with you, beyond obviously the technical skills?
Yeah, I think the technical skills are very, very important, but a lot of our students in our universities come with that. I think that what I try to do for them is uh, explain to them, or help them become better researchers and ultimately better independent researchers, so they could then run their own groups in the future, either in academia or industry or startups or whatever they choose to do. So the main thing that I try to focus on is help them with problem selection.
Hmm.
Uh, and I also feel very strongly that the PhD should be completely owned by the students. So even in projects where I'm very heavily involved, I try to stay away from telling them or proposing the complete solution. As far as the PhD thesis is concerned, I think ownership matters. I think it also develops a lot of confidence
Hmm.
in the student. So I have a few things that I pay a lot of attention to. I try my best to give them that early win as a PhD student because that worked for me. I was a very diffident student in the beginning. I thought I was smart, but I looked at all these other people and they all seemed a lot smarter. They seemed a lot more productive. And I think all of us are comparing with other people. And I was like, what is, how do I get better. And then it took me my first paper, which I feel I led or worked with some other students on, and it was a satisfying piece of work. And then that confidence just grew, right? And I think it's true for a lot of students.
Yeah,
And so I try to give them an early win. It has to be earned. It's not like I tell them exactly what to do and solve the problem. So
sure.
you give them that early win and then develop their confidence. And then I spend a lot of time to figuring out whether the problem they're choosing to work on is the right problem, whether it's going to have matter in the future or not. And I don't care about whether the paper is going to get accepted or not. And maybe that's a problem because we have our share of rejections. But for me, it's much more about an internal compass that we all have to believe in what we're doing and we understand why we're doing it. Because I'm confident that if the problem can be solved, our students are capable of solving it. It's much more difficult to figure out whether the problem is worth solving.
Yeah, that makes a lot of sense. So, moving forward a little bit from when you started at MIT to, let's say, 2001, it was the year of the big dot-com crash. Google was, what, 3 years old? Started in 1998, I think. The internet's first big hype cycle was over, something we should all bear in mind right now with the hype that's going on. And suddenly, all in the same year, right? So it was right in the middle of this dot-com crash. There were the first 4 papers were all published about distributed hash tables, about DHTs. For those of you not familiar with DHTs, they store key value pairs by assigning keys to different computers or nodes, and a node stores the value for all the keys for which it's responsible. And it's designed to be very scalable in a distributed fashion. And the idea is to spread the load across all the nodes in a fault-tolerant and scalable way. You co-authored Cord, which was one of those papers, which specifically sort of specified how keys are assigned to each of the nodes using a very simple, sort of elegant circular ring, and also how a node can discover the value for a given key by first locating the node responsible for that key and then routing that request using successors in the ring. So you co-authored that paper with Jan Stoker and Robert Morris and others in that at that time. And in the same year, as I mentioned before, the pastry, tapestry, can DHT papers were published. So you got to ask what was in the water at the time. What was in the air, really? What was in the air that meant that suddenly there was a realization that this was going to be a problem that mattered? Because I actually think that there was probably a lot of people that just didn't understand where was this coming from. So what was motivating you and presumably the other groups too?
Yeah, what was motivating us was the advent of peer-to-peer computing, um, which was the idea that you have all these machines on the internet in people's homes and offices, etc., and they could collaborate. Now, this was before the era of data centers. And today you have this kind of highly distributed computing happening, and the legacy of that work is in these big data centers with hundreds of thousands of machines. In those days, the hundreds of thousands of machines were in people's homes. And I believe in
Hmm.
2000, an undergraduate student at Northeastern, Sean Fanning, came up with an application called Napster, which,
Yep.
depending on your point of view, either revolutionized the music industry, or was the most anarchic thing or the most illegal thing happening on the internet. And it was an interesting system. It basically allowed for people to share music files, and they could download music files from each other's computers and get rid of this bottleneck. Now, it was also there was a small matter of the illegality of it, and eventually Napster got shut down because it had a centralized directory that kept track of which music was on which laptop, which user's computer in their homes or
Hmm.
offices.
Hmm.
And at the same time, there were other systems that were being proposed in the world, not by academics or maybe by semi-academics. The one was
Hmm.
Nutella, which had all these files that were being distributed. And so what was in the air was a lot of the equivalent of stick it to the man, the idea that the internet should not be controlled by a central entity, and it should be, highly decentralized and democratic, and people should be allowed to publish whatever they want without going to a central website. It's a little funny when you think about what has happened to the internet today,
Yes, of course.
with excessive
Yeah.
centralization, at least the logical centralization, with the exception of things like Bitcoin.
Hmm.
But in any event, the two systems that motivated a lot of us, at least for us at MIT in this project, were Nutella, which would broadcast these requests and was not very efficient, and you couldn't sometimes find the items we were looking for. And Freenet, which was a fantastic
Oh, yeah.
invention, a
Yeah.
system which was about
Mhm.
anonymous publishing of information in a censorship resilient way. So what was in the air was this idea that if it was highly centralized, it could get shut down, it could be controlled by specific entities like companies that, really should not own everything. Again, all of this stuff sounds a little archaic, but that was the idealistic view. And this work on DHTs came about because we wanted to get, like good academics, we wanted to get provable guarantees on the retrieval of objects you were searching for, ideally within a finite or a bounded amount of time. And the problem was the needle in the haystack, which was this heavy tail of items you're searching for that very few other people want. If it's very common stuff, it's going to get cached everywhere. You're going to find it. But there were lots of items people were searching for that were not widely popular, but you still needed it. People understood heavy tail distributions by that
Yeah.
time.
Hmm.
And
Hmm.
that's what was in the air. So we did not know when we were building CORD. I mean, there was CORD, the first CORD paper in the system was somewhat unique for an academic piece of work. There were no students involved. Jan had just graduated from Berkeley, and he was I'm not sure if it was a formal or informal postdoc, but he spent a semester with us at MIT, and we started talking about a bunch of ideas. And one of them was kind of very simplistically, could we build a distributed system that would have the nice properties of a freenet with highly
Hmm.
distributed data storage, but provide bounded guarantees on retrieval. And there were two parts to it. One of them was this ring idea to quickly retrieve items with the skip list like data structure. That my recollection is really that we were all working on it. I think David Karger had the key insight in the actual algorithm that we were batting around a number of different ideas, and this idea of a ring was around with consistent hashing and so on. There are many ways to do consistent hashing, but this ring idea and the skip list, I think David should deserves a lot of credit for that.
Yeah.
And people like Robert and Jan and myself and Franz was kind of all of us worked on all aspects of the system. And I spent a lot of time on stabilization, which turned out to be a difficult and very intellectually interesting problem,
Right.
which is as nodes come and go, how do you keep the data structures intact?
Yeah.
So I think there were two
Yeah.
distinct but very related parts to the project. And the distributed stabilization protocols ended up being quite interesting to work on once we had the fundamental data structure.
So there was this whole question of the consistency model and the stabilization mechanism. About 10 years later, you probably remember there was a sort of interesting paper from Pamela Zave who was talking about how um, the chord protocol in practice doesn't necessarily become eventually consistent, at least not in its originally published form. And luckily there was a pretty simple fix, which I expect many people found out when they actually tried to use it and deploy it for themselves. And we've all been that, right? We've all published papers, and then someone comes and asks the question, and you sort of think, "Oh crap, is it all going to come crashing down? Did I actually miss something?" Forces you to rethink. It's easy to become a bit defensive, and then you start thinking about, okay, you know, what is the way to sort of correctly interact in an environment like that? And I think it's a very important part of academia. We've done some experiments like that with a class that we teach at Stanford, CS 244, where we have these reproducible students have to reproduce a paper that's been published. And then if they find something that they don't understand or they disagree with, they go contact the original authors and then have a conversation with them. And, that could be pretty daunting that you go to some well-known member, sort of professor in the field and say, hey, that paper you published 15 years ago? I think it was wrong. I think I couldn't reproduce it. Or, here was the things that we struggle with. And I'm kind of curious, the, do you remember that incident with that particular incident? But more generally, have you sort of developed a way to approach this?
Yeah, well, I do remember it. And right after it came out, Jan and Stuck and I spent a bunch of time, and we kind of convinced ourselves that these were corner cases, that some of it had to do with when a node leaves the system and comes back with a different ID. That was one example of a case. I mean, a number of people had built systems and applications and had tried them out on the internet or on simulation with Cord, and we didn't feel like it was fundamentally broken, but it was very interesting. The paper was very interesting. I liked the methodology that Pamela Zeeb used was really interesting in terms of the work. Insofar as whether it was all going to come crashing down or not, um, on the one hand, you're very curious about what it is that's being said about the protocol. On the other hand, we were fairly confident. A lot of people had built applications and had tried them out, and it didn't seem to have, really been catastrophic. People could still find items, and
Yeah.
it was there. Now, there were a few things about the way we would write these papers that I think matter, which is that the original Cord paper and even the journal version of the Cord paper had these theorems that were said, and not all the theorems were proved in complete detail. And the original
Mhm.
Cord paper has a particular failing, which is it points to a technical report that we were actively working on, but never actually got published with all of the proofs. I think there was some technical report reference, if I'm not mistaken. The journal version is much more detailed. And then there was a paper in 2002 at PodC, the Principal Distributed Computing Conference, that actually laid out a number of the results in more detail. So, it was sort of a more of a confused mess, but in terms of there was not a very definitive specific paper, but there was an implementation or multiple implementations. Yeah, it's part of the business. You're always wondering whether something you said is not turns out to be inaccurate later. Um, and yeah, fortunately, I think there was a fairly straightforward set of fixes around how you manage identifiers. Uh, but if something
Yeah.
breaks, it breaks, and what
Yeah.
matters is whether what the actual truth is.
So I can't leave the topic of Corb without pointing out for many people will know this already, but I mean it's become one of the most widely cited papers in all of computer systems. It has 19,000 citations listed on Google Scholar, which is pretty incredible. And I might add that that's actually only your second most cited paper after your paper on low energy scheduling and processing for sensor networks, which has a staggering 22,000 citations. In fact, you're one of the very, very few people in the field that has four papers with over 10,000 citations. Now, we don't want to over-index too much on citation, but they are a good indication of the level of interest and the level of community that new papers and new ideas have spawned. And so I'm sort of curious, if you look back with hindsight, they were all in topics that became very big, clearly. They created their own community and sense. But what was it about picking the problem and writing the paper that you could sort of point out that might be useful to others to learn about?
Yeah, I think a lot of this is because they were one of the earlier papers in the field and they said things that were, I think, useful. But the other important thing about it is that I think I tried this in in all my papers if I can. I think, and I know you do too, because I enjoy reading your papers and I mean, some other people in the community. I think we have to write papers that are really easy to understand and that say things in the simplest possible way, and then they build a story, they build one concept on top of another concept. So the papers have to be written to teach, not to show
Hmm.
off how smart we are.
Yeah.
And this is a bit of I think this is actually a good way to write papers even in the stage of submission. But sometimes you get these reviews that come back saying, well, it's obvious or it's simple. And well, the fact is that if it's new and it turns out to look obvious, it doesn't mean that it's unpublishable. But when you write it in a way that's easy to understand, it comes across as simple. So what happens, I think, I've seen some papers that come in that make it actually hard to understand. There's gratuitous notation, there's needless math when you have to communicate the intuition first before you get to maybe the mathematical notation. There's pseudocode that's very complicated to understand without the intuition. And I think sometimes we do this because we would like to communicate to reviewers that it's deep and therefore the paper should be accepted. So for me, the philosophy, I think one of the reasons these are well cited is one, their earlier papers, but the other is I just think they're easy to understand. They're not that hard to understand once you read it, and maybe that's why people like citing it.
Yeah, maybe. I mean, they're simple and clear. I mean, yes, simple ideas, but clearly articulated, and I think that's key, right? Which is,
Actually, one example, I mean, I won't embarrass you, Nick, but your paper on sizing router buffers,
hmm,
uh, the thing that showed that when you have many different n connections that are unsynchronized, you don't need a bandwidth delay product, but it's like 1 over square root of n. I mean, that's an example
yep.
of beautifully written paper. It just tells a great story with a practical important result, but it doesn't overcomplicate it. You could have gone and written a paper in a different way, which is a lot of math without the intuition.
I mean, I think it's true that for uh, we've all had reviews that say, oh, this idea is too simple,
Yeah.
and you've probably had rejections that say this idea is too simple, and
If you remember, I'm sorry, the open flow paper that you led, I think we decided not to submit, if I'm not mistaken, just not to submit to SIGCOMM because we thought people would reject it because it was too simple.
exactly, that was exactly
And
right. It was an
and it's
unreviewed technical comment.
that is such, I mean, my view, a failure of the system that we have because yeah, it's simple, but it's beautiful and important. And I mean, I remember this discussion on an email thread where basically majority of the authors concluded that it probably won't get in, so why bother?
Yep. No, I think that was very true. So no conversation with you can be complete without talking more about congestion control. We touched on it for wireless case, but you've also done a lot of work on congestion control for wireline networks as well. And so, a lot of it is, of course, going back and trying to fix some of the many limitations of TCP in specific environments. Um, but you had done this work for that was back in I think about 1999 2000 on the congestion manager, and the idea was that there would be many TCP connections on the same host. Probably little did you know at that time how many there would actually be, and could you share that knowledge of the congestion between those flows so that they could benefit from each other without actually having to go out and find that for themselves, so they could proactively ask each other and share that information. And when cloud computing came along, lo and behold, this became sort of hundreds or thousands of TCP connections sharing the same host at the same time. So, with hindsight, how did that sort of connection management idea evolve over time? And if you look back, actually, was it the right way to do it? Did it evolve into something that was sort of based on that? How do you see its progression?
Yeah, I think that I mean, for me, it's just led one step to the next. I think that that idea, I don't think has had the sort of impact on the real world that I would have liked. Like, I don't. I think it would make a lot of sense for like a system like Google to do something, and maybe they're doing something like that. I'm not sure, but I haven't heard about that. It would seem to make a lot of sense because you can leverage the information you already have, having created a map of the internet, like these systems like maybe even Espresso or the big data centers based, the output streams coming out of these big data centers. To me, it would make a lot of sense. It's very intuitive, but maybe
Hmm.
it probably hasn't had the impact that it has. Whereas some of the more specific algorithms that came about, like
Yeah,
binomial congestion control
I
or
know. I was
something
going to
like
ask you about that next. Yeah.
implemented.
Yeah.
So how did I come up with these areas? It just felt like the right problem to work on because there's all these connections sharing, not sharing information, and they're each learning about the state of congestion. So why not share it? And then when you take that idea, there's immediately it comes up with some interesting problems to tackle. And I don't know if people at Google or Amazon or anywhere else are listening. Uh, it'd be really good to try
Anything
out
along those
something like the
lines. Yeah.
congestion manager.
Yeah. I mean, there was a long line of congestion, so basically congestion management, congestion control papers that you wrote after that. Starting when Deepak Bansal was a student, and the binomial congestion control, allowing AMD equations to be modified based on specific context. So again, it was about the context, about different environments in which TCP would operate. And then, of course, all the way through then to with Keith when he was a PhD student with you and using computers and machine learning to explore a sort of a whole space of congestion control protocols. Um, and so instead of that normal kind of grad student trial and error of, okay, let's publish another paper on congestion control, I say, actually, we'll let the computer go and explore the space, which can be done much faster and much more efficiently. And then there was COPA, delay-based congestion control algorithm. So it's been this sort of long path of different things that were in different times and different contexts. Can you tell us a little bit about that journey along the way that led you to sort of that cycle of experiment and then through to the computer generation mechanisms and with Remy a little bit later?
Yeah, so in the early 2000s, I worked on these algorithms like binomial, and then when Deepak went to Microsoft, Bansal, he put it into compound TCP, and they found that it's actually useful as one of the many modes. And then I stopped working on it for some period of time. If you remember, in our community, it became unfashionable to work on it, and even a paper like RCP that you and Nandita came up with, to me, is one of the most beautiful ideas, and that was an example of where we got away from it, right? It was hard to publish these papers or get people interested. But I think the revival happened in the early 2010s when two things happened. One is that three things. First of all, I think the variety of applications on the internet grew even more. People became very, very interested in commercially interested in different applications like video applications and web based applications performing really well because everything ran on top of HTTP, or many things ran on top of HTTP. Second, there was a big awareness of the importance of performance. And this came about because of these large providers, and they would write these papers about tail latencies or tail delays and how 1 millisecond or 7 milliseconds extra would lead to a certain percentage of people stopping to use the application. I don't remember the numbers, and the third is the technology change, right? We got data centers, we got wireless became much more heterogeneous in terms of like LTE that came about, and yet it had problems. So this combination of things meant that people cared about application level performance again, and that led to Remy was really about how to optimize a combination of throughput and delay for heterogeneous applications like video conferencing, web page load times, and so on. So that then led to looking at it in terms of utility functions, which is an old idea from Frank Kelly and others,
Yeah.
but a more practical and in a more end-to-end context where it's not about the routers setting shadow prices, but it's about coming up with end-to-end algorithms for tackling that problem. And COPA came about from that ethos of looking at it in terms of application level utility functions, trading off throughput to delay. And COPA actually has become deployed at Facebook. I believe they use it for mobile uploads of video because they just run these big properties now can take all these algorithms and run end-to-end experiments and A/B tests and try out what works well in what scenario. And that led to the congestion control plane idea, which was this platform where you could have many different congestion controllers easily implemented so that the system could then not pin to one, but just pick one of many. It could be BBR, it could be COPA, it could be Vegas, it could be whatever, depending on the conditions at hand. So that's really the story here, but it comes down to optimizing application level utility functions.
In the chat, John Crowcroft mentioned that, of course, that the congestion managers probably found their way through to what's now the bandwidth brokers, and that sort of sharing and pooling of information that's used there. By the way, if there's anyone else got any other questions, just pop them in the Q&A. We've only got about 5 or 6 minutes left, so I'll probably get to one or two questions. I just want to move on a little bit and talk about your entrepreneurial activities. You've been involved in a number of spinouts from MIT, most notably CMT, or Cambridge Mobile Telematics, which grew, I think, out of the Cartel project, right? That you had many years ago. And you've been involved in advising many companies, helping students, starting your own along the way. I know you're thinking about doing something new at the moment, and I'm sure there are many. There are many other startups that you've helped and advised along the way. So how do you think about the transition from the research that you're doing into something entrepreneurial? You get the wonderful opportunity at MIT to be able to do that, step out and step in. Clearly, Stanford's like that, and Berkeley and many other schools as well get that sort of opportunity to step in and out. But it's very time consuming, and you have to decide, what am I going to go do that? After all, you're an academic, and so you want to come back and sort of teach and have PhD students. So how is that for you? How do you think about it? And then how does that affect the sort of the process of how you wrap up the research project on campus and then transfer that off into whatever you're doing next?
Yeah, that's a great question. So for me, the cartel to CMT story was quite revealing, which is we'd got a lot of academic successes, and the press was writing about our contributions here. We developed one of the things we've done was a pothole patrol where we mapped every day um, the worst potholes in the Boston area by
Yep.
instrumenting taxis in Boston with our devices. And every week we would publish a website. And then it reached a point in the project where you could not make further progress in academia. You needed scale. You needed to have people use it. And there's multiple ways to do it. You could open source a bunch of stuff out, but something like Cartel, you could open source it out, but you needed a deployment, you needed users, you needed applications that people could use. So there, the startup was the only viable approach because I had tried to get large companies interested in it, car companies and so on, and it was just impossible. And
Yeah.
I understand now why. I understand that the way large corporations work is, if it isn't a 1 billion or $2 billion business for them, they're probably not going to take the risk in the near
Right.
term. And if they
Yeah.
see a path to that, but many of these things, there's no path. That's why startups exist. People buy from startups not because they want to, but because they have to.
They have
Uh,
to. That's right. Yeah.
yeah,
Yeah.
and if
Yeah.
you are coming up with something like that, I mean, no one, I mean, it's a really bad idea to buy products from a startup. So the
Yeah.
startup had better build something that is truly valuable and unique that you can take a chance on it, right, as a company. And that's why one should commercialize. And that's not necessarily the only way to make impact. I think open source is a great way to do it. Influencing standards and getting it into a big company's idea is a great way to do it. There's many ways to have entrepreneurship. But I will say this, networking as a field is actually led to an unusual number of good founders, successful founders in other areas. You look at like the Databricks as an example.
Yes.
And,
Right.
I was talking with Ali Ghodsi about this
Mhm.
a couple of years ago. And, it's interesting. It's because I think our field is deeply ambiguous, involves a lot of people, involves politics, involves organization. And you take BGP and, you teach about how BGP works with ISPs that have to compete and yet cooperate. And you kind of understand that the real world is really messy, that you have to come up with a proposition that's a win for everybody and yet disrupt somebody. And I think that our field teaches that, and I think it's well set up for
Yeah.
entrepreneurship.
Yeah. My own experience with starting companies was after we tried and then failed to give the ideas away for free to industry because they wouldn't take it. And I think early days we just couldn't understand why they wouldn't take it. It seemed obvious to us and seemed like a complete winner. But you're absolutely right. Unless it's actually going to be a very, very large business, then it's not of sufficient interest. And the only way to do it, if you've got the passion to do it, is then to take the idea forward. Okay, so we're running out of time here, and so uh, I'm going to ask you one last question from that I had for you. So you love ball sports and racket sports and cricket and basically anything with a ball that moves fast, as far as I can tell. I know you like to beat your students at squash.
That's a long time
So,
ago.
but you're gonna have to blame your sister Hamza for telling him about this. I didn't actually know about your prowess in pickleball. You've competed in some tournaments, and even now you're a national title holder. So tell us the lowdown here. What happened?
Yeah, I love these racket sports. And I used to play squash with my students, and then I stopped because I just moved away. But I picked up pickleball about a little over 2 years ago and started competing, and I love it. I spend a lot of time, on it. And I competed in the national senior games. So I'm, in the 50 to 55 category and ended up in my level getting 3 gold medals. So I was
Cool.
super
All
thrilled
right.
about that. Yeah.
So I'm not sure which is better, the four papers with more than 10,000 citations or the national medals in pickleball. That's a pretty
I
good.
think I think the most valuable thing is honestly the most valuable thing are the success of my students. I think that's what I would like to be remembered about.
Great. Okay. We're exactly out of time, and I was told we have to wrap up exactly on hour because many people have to go on to other things. You probably do too. So I just wanted to say thanks ever so much, Harry. It's been a great opportunity to get to know you better, and a little bit about what makes you tick. Yeah, I've done 3 or 4 of these interviews now with Amin and Jen and you, and it's sort of interesting the sort of the provenance and the background that complete three people with completely different sort of stories and backgrounds that led into the field that we all know and very familiar with, and I think it's going to be great to know that the things that got you there along the way. I actually had about 15 other questions that I was going to ask you, but clearly there isn't time to do that today. But I want to thank everybody for being here. Remind you that there's going to be another networking channel in 2 weeks' time. And thank you again, Harry. I'll see you soon.
Thanks for having me. Bye.